All right. So in the last lecture, I talked about the step size and why it is important. But in order to understand the structure of that, we need to define some concepts and definitions such as beta smooth of a convex function, and also another concept which is strongly convex concept. So smoothness is different in different contexts, but the definition that we use for convex function, smoothness of convex function that we care about, is that a function is called, a function f is called beta smooth if its gradient is Lipschitz continuous. It means that gradient of x minus gradient of f at y is less than or equal to beta times x minus y. So we call it beta smooth. F is beta smooth. So our claim is that if f of x is smooth, then beta over 2x squared minus f of x is convex. So in order to prove that, we recall that if a function is monotone, then it is straightforward and it is easy to show that it is convex. And so we just need to define a function g of x, and here, for example, we call this function g of x. This is g of x. And we just need to show that it is monotone. So gradient of g of x minus gradient of g of y times x minus y. So we just need to show that this is greater than 0. And so beta x minus y minus gradient of f of x minus gradient of f of y times x minus y. So this is just the definition of g of x. G of x gradient of g of x minus gradient of g of y. So this one is this one is exactly the same as saying that this is the norm of this x minus y minus gradient of f of x minus gradient of f of y times x minus y. And this one is greater than equal to beta x minus 1 minus gradient of f of x minus gradient of f of y times x minus y. Why? Because we have just used the this inequality, Cauchy-Schwarz inequality, that the inner product is less than equal to u and v. So we have used the Cauchy-Schwarz, and so this one is greater than beta times x minus y minus beta x minus y times x minus y. So this is, you see, this is equal to 0. And so we have proved that G is monotone. and therefore G is convex. So our proof is now complete. So we have shown that G of x, this G of x, which is defined by x2 minus f of x, is convex, and by definition of convex function, you can write G of y is greater than equal to G of x plus G of x times y minus x for any y. And so we can just use the definition of G of x, and so for G of y we can write y squared minus f of y, and this is greater than for definition of G of x, which is x squared minus f of x plus, again, the definition of G of x, gradient minus f of x plus beta x minus gradient of f of x, y minus x. So if you just simplify this, you can write that f of y is less than equal to f of x. I just try to simplify that. Gradient of f of x times y minus x plus beta over 2 y minus x squared. And one more time, f of y is upper bounded by f of x plus gradient of f of x times y minus x plus beta over 2 y minus x squared. Okay, so this has great geometric intuition, and that's this, that if you have a function like this, so f of y, it is your function, you can fit a quadratic on top of it. So this is my quadratic that I fit on top of that. So at this point, we can fit a quadratic. So it is upper bounded by this blue quadratic function. And also we can show that if f is twice differentiable, we can say that f is convex if and only if the Hessian of f of x is a positive semi-definite. And also, if f is beta smooth, you can easily show that gradient of f of x is lower or equal to beta times identity. So let's go and see the failure of smoothness. So when you have an absolute function, okay, at this point you can upper bound it by a quadratic function, but at this non-smooth point you cannot upper bound it. So this is a problem. And I give you an example that if f of x is the quadratic function, then f of x is beta smooth for any beta which is greater than 2 lambda maximum q. So another concept that I want to talk is, first I define what is a strongly convex function is. A function f is strongly convex if parameter alpha with parameter alpha, if g of x, f of x minus alpha over x squared, if this is convex. So a function f is strongly convex if g of x is convex. And let's just use the definition of convex function, which I can write as follows: g of y is greater than equal to g of x plus gradient of g of x times y minus x for any y. And because I have defined g as that, I can write f of y minus alpha over squared is greater than f of x minus alpha over 2 x squared plus gradient of f of x minus alpha x times y minus x. So now we are doing an opposite result. We say that f of y this time is lower bounded by a quadratic function. So f of y is greater than equal to gradient of f of x times y minus x plus alpha over 2y minus x squared. And this is the standard convexity, and this is the definition of strong convexity. Strong convexity. But here is just the standard convexity. So you see that you have a function like this. You have a function which is highly nonlinear, and you try to approximate it by a quadratic function. So, for example, at this point, x and f of y is here. So your quadratic function, function f, which is the red line, is lower bounded by a quadratic function. Last time you see it was upper bounded when we talk about the beta smooth function. Now that we have defined the strong convexity, we have come up to an inequality that shows how we can lower bound it by a quadratic function. So this blue line is the quadratic function. And so it guarantees that your function grows when you move away from the optimal solution. Same for gradient, because since the gradient of the quadratic is very steep, so when you go far away from that, and then so it is steep as well, and also the Hessian is greater than alpha inequality, alpha identity times identity.